So, good morning, children. Let us continue our topic. So, we have discussed in the previous session about the versatile nature of carbon, isn't it? So, how carbon is able to form numerous compounds, and what is this ability called as catenation. So, now we also know that carbon exists in abundance in nature, in the sense in its various forms. Fine. So, one such form is what? The free state, which is termed as allotropes. So what are allotropes? The molecules of a single element that differ in crystalline or molecular structure. Now these allotropes, be it any element, they would be physically different, but chemically their properties would be similar. Why? Because they are of the same element. Now this carbon alone is not a element which exists in the allotropic forms. There are some other elements also which show this property of allotropy. Now, so some of the examples: phosphorus, oxygen, sulfur, boron, silicon. Okay. Now, I hope you can recognize the allotrope of oxygen. You have learned in your biogeochemical cycles of 9th standard. Yes, O2 and O3. That is the molecular state, dimolecular state and trimolecular state. O2 and O3. Oxygen and ozone. Similarly, phosphorus also exists in various allotropic forms: velvet phosphorus, red phosphorus. Okay. Then even sulfur, rhombic phosphorus, rhombic sulfur, amorphous sulfur. Clear, children? So we will just now focus on the two main allotropes of carbon. Now, before we talk about the two most important allotropes of carbon, let us know how many allotropes of carbon exist in nature. Now, altogether there are 8. Some have been mentioned here on the screen for you. Now, there are actually two forms: the crystalline form and the amorphous form. Amorphous in the sense powdery form, which we see in our daily life. That is coke, charcoal, carbon black, soot. All these are what, children? The amorphous form of carbon, amorphous allotropes. Then coming to the crystalline nature, the graphite, diamond and fullerenes. Okay, children? Now, we will be now focusing on the three most important allotropes of carbon, that is the crystalline, that is graphite, diamond and fullerene. So let us just view the structure. Now the first allotrope, the very common, and we are all familiar with this name, diamond, isn't it? Now, what is its most important use? We all know, yes, in making jewelry. But apart from making jewelry, children, it is used in the various industries, especially in your as a cutter. Okay, so because a diamond can be used as a cutter or in the laser as a laser beam. Clear, children? Then now this diamond, how is this diamond? It is, if you observe now, one carbon is linked to 4 other carbons. Okay, as I told you earlier, carbon will never transfer electrons but rather share. And how many electrons does a carbon have? 4. So that's why carbon is what? A tetravalent. And each electron of one carbon will be shared by another carbon. So that means 4 electrons of one carbon will be shared by 4 different carbons, which in turn will be linked to another 4 carbon atoms. Am I clear? So now, thereby what happens, if you see now, they form a tetrahedral structure. Now this tetrahedral structure will give rise to a cage-like pattern. Now here, if you view, children, so one carbon linked to 4 other carbons. Now, since one electron is shared between 2 carbons, that is why it's what kind of bond? A single bond. That means the electrons are satisfied. Am I clear, children? And it is this, because of this reason only, this complex structure only, diamond is hard by nature. Highly dense, highly hardest substance in nature, the non-metallic hardest substance. Am I clear, children? And then, since it is very hard, obviously the melting and the boiling points are also very, very high. Its boiling point is very high. Okay, children? So since the carbon does not have any free electrons, it is a very bad conductor of electricity. Okay. So carbon tetrahedral structure has each carbon bond with another 4 carbon atoms. Am I clear? and having each of these will have what kind of bond? Single bond. So now let us move to the next one, that is graphite. Now here observe, in case of diamond you had one carbon being linked to 4 other carbons, isn't it children? But here it so happens that a single carbon is linked to three other carbon atoms. Every carbon is here linked to 3 other carbons. So you see there is one less, in the sense out of 4 electrons only 3 electrons are getting satisfied. And then where would be the other electron? That other electron will be again shared between the 2 atoms to form a double bond. About that we'll discuss later. So remember, in graphite there is one carbon bonding with how many electrons? 3 other electrons. Am I clear? So thereby what happens? They are going to bond to form hexagonal rings. So now if you see children, the main difference between carbon and diamond is, in carbon all the 4 electrons are shared. But here in case of graphite, 3 electrons are only being shared where 1 electron is free. Am I clear? So that means graphite has a charge. Clear? So due to this charge only, the graphite is a good conductor of electricity. We all know electricity is conducted by the charged particles. Hence, graphite is able to conduct electricity due to presence of one free electron. Then let us compare the structure. If you see now, in case of diamond was a tetrahedral cage-like structure. But here in case of graphite, these are hexagonal, arranged in layers. So that's why you all know graphite, in your pencil leaf, it will be very powdery in texture, isn't it? And thereby very slippery. The reason is the hexagonal rings, which are like sheets, will be linked to another layer of sheet below each other with very weak forces, which are called as van der Waals forces. About this you will be learning in your higher classes. So remember, now the bond between one carbon to another carbon is very strong. But the bond between the one layer of hexagonal sheets to the other layer of hexagonal sheets is very, very weak. So that's why graphite is very soft and slippery. And it is also a good conductor of electricity. Now here if you see the model, so it will be hexagonal. And each carbon, if you see, will be linked to another 3 carbon atoms. So now just let us see the comparative structures of these diamond and carbon. So if you see, diamond looks like an enclosed structure wherein every carbon is bond so closely that they don't have any free electrons, hence and the bonds are very strong. That's why they are very hard. But come here, over here, in case of your graphite, they are loosely bonded to one layer to the other, hence they are very soft and slippery. Hexagonal but not very compactly arranged. So these are the major differences between diamond and the graphite, children. Hardest, soft and slippery. Poor conductor. Why it is a poor conductor? Because all the 4 electrons are being completely shared. Hence, there is no charge on the diamond, on the carbon particles in diamond. But here in graphite, they are good conductors because of the presence of one free electron. So that means there is a charge which allows it to conduct electricity. Tetrahedral, cage-like, compactly arranged. Hexagonal, arranged in sheets, bond with very weak van der Waals forces. Here, so if you see here, now each carbon has 4 covalent bonds with 4 other carbon atoms. Here only 3 covalent bonds with 3 other carbon atoms. Now, let us come to the third kind of allotrope of carbon. Now, you can say this is the very latest discovery. Now, if you see, children, carbon and graphite are n number, infinite. They can be of any number of carbon atoms. But in case of fullerene, this is limited to only 60 molecules. How many molecules? 60 molecules. Now this 60 atoms of carbon are combining to form a ball-like, a football-shaped structure, which is called as fullerene. Now if you see here, you all must have seen the patches on the football. What would be their shape? Yes, a pentagonal and an hexagonal. So this also is going to have pentagonal and hexagonal rings which are going to be interlocked to each other, thereby giving a closed structure. Okay, now very interesting story is there behind the naming of this fullerene compounds. About this you will see in the video, children. But remember, the smallest allotrope we can say of carbon is fullerene. With how many molecules, sir? With how many carbon atoms? 60. So C60. Now just I'll play video here, children, for your better understanding.
Allotropes according the element hexagonal rings. One of these bonds is a double bond, and thus the valency of carbon is set.
So now I hope, children, now you are clear with the allotropes of the carbon. So in the next session we will continue with what are the types of covalent bonds. Please kindly go through, children, and one more humble request, children, kindly submit your art integration projects. Thank you. Have a good day.